Welcome to Data Science with EJD. We are talking about data science in general, and as we kept moving, we stumbled on machine learning, and we saw machine learning to be that situation where um, machines, just like the name implies, learn from data, so that with more data they can make better decisions as they keep learning from data. So it is different from the normal modeling we have, where you can say a function depends on the particular thing, and those things keep going on like that. So this is a bit different from that kind of thing. Okay, and as we went on, we discovered that machine learning is subdivided into three major aspects: supervised learning, unsupervised learning, and reinforcement learning. And for supervised learning, there you have machine learning from labeled data. And when we talk about labeled data, we are talking about data that you can partition into inputs and outputs. The inputs are called features, while the output is the target. For instance, we are determining the growth rate, the growth of a person, depending on so the growth in that case will be the target, while the features will be things whatever growth depends on, like say nutrition, genetics, and environment, and so on and so forth. Then and we say that the key algorithms under supervised learning are classification and regression algorithms, and they have different specific algorithms under them. And then we move on to unsupervised learning, where machine learns from unlabeled data. And when we talk about unlabeled data, we have just the inputs without output, so to speak. We have just the features without the target, because what we're basically looking for is that from the data, we want to see patterns, we want to see you want to just see patterns, how some of the data points behave together and things like that, or whatever they have in common. So, and the key algorithms under unsupervised learning, we've seen them to be things like first of all, clustering. After clustering, we saw dimensionality reduction, where we saw things like PCA and TSNE and all that. Then we also went ahead to see association rule, association rule learning, where we have had things like market basket analysis, a priori algorithm, and of course frequent part growth algorithm, FP growth algorithm, right? And for the last few videos, we've been looking at reinforcement learning, where you have an agent in a particular state taking certain actions leading to certain rewards, and it keeps changing like that, right? So here we are looking at model free control in reinforcement learning. Okay, in some reinforcement learning situation, you have all the necessary information, and in that case, you can use things like dynamic programming because you have all the necessary information. But what if you don't have all the information you need about the environment and all that? All right, that's why we look at things like model free control. In fact, the last video talks about model free prediction or something like that. There we saw Monte Carlo prediction, and there's another one. I think we're still going to come across it in this place also. Um, Monte Carlo prediction and temporal difference prediction, exactly. So that's when you don't know all the necessary information you need to know, and then you still go ahead. So by way of introduction, model free control methods are essential algorithms that allow an agent to learn an optimal policy directly from interactions with an environment without requiring a model of the environment's transition probabilities or rewards. So you don't have information about the environment already, but by interacting with the environment, then you can now begin to make your own decisions. So these algorithms estimate the action value function Q of S, comma A, and derive policies from it. So of course that function is dependent on the state and the action taken at that state to get the action value, right? So, and then we move on to talk about exploration versus exploitation trade-off. So, exploration versus exploitation trade-off. So, the core challenge here, we have two challenges. We need to explore and we need to exploit. So, exploration is trying new or less known actions to discover their potential reward. So, you don't know, you're in a new environment, you don't know what to expect. So, you just begin to check things out, and then begin to say, oh, okay, this, if I do this, I get this reward. If I do this, I get this reward. So it means if I want to get this reward, the best reward, this is what I should do. That's the idea of exploration. Exploitation is using current knowledge to maximize immediate reward by choosing the best known action. So that means that as you explore, you find best ways to do certain things, and then you can now begin to exploit your knowledge to do that. So the importance of this whole trade-off, but then we need a trade-off between both exploration and exploitation. So the importance of that trade-off is this: that if you solely exploiting, if all you are doing is exploiting, maybe you get to a new environment and you know how to do some things very well. So if you now depend on just the few knowledge you already have, so solely exploiting might trap the agent in suboptimal behavior. So you may not always get the best. Maybe you already know the best way from here to that place is this. There might be a better way than that, actually. So if you don't also try to explore once in a while, though having if you have explored already and you think you have all the things you need, so sometimes you should also give yourself some opportunity to learn new things so you can get better ways of doing what you think you are doing very well already. So solely exploiting might trap the agent in suboptimal behavior, but then excessive exploration, all right, can delay convergence. So the fact that you want maybe in a bid to always get the best, you want to keep exploring and you're wasting time. So you need to balance between exploration and exploitation, right? So explore as much as possible. Once you think you've got your values, begin to exploit. But once in a while, give yourself new opportunities to also still explore to see if there are better ways of doing what you're currently doing. Because excessive exploration can delay convergence to an optimal policy. So there should be a trade-off between the two. The strategies for balancing between exploration and exploitation include fixed epsilon-greedy. So here you have random exploration probability epsilon remains constant, and you have decay epsilon. So you start with high epsilon and gradually reduce it. Other methods include soft marks, upper confidence bound, Bayesian methods, beyond which is beyond our scope in this situation. So for the epsilon greedy policy, right, this is a simple yet powerful approach to balance exploration and exploitation. So for each step, you have the policy of an action given a particular state, and that is given as the equation you have right there, where epsilon is the exploration rate, which is typically small. In mathematics, right, especially when we talk about things like limits and all that, epsilon or delta is usually a very small positive value. So it could be 0.1, which is 10 raised per minus 1, or it can be 0.01 or 10 raised per minus 2 or 0.001, which is the same thing as 10 raised per minus 3. So small number, but positive, right? And the absolute value of A is the number of possible outcomes. So that's the A you're seeing in this expression right here for that policy. So the pros and cons, right? So the epsilon greedy policy is easy to implement. All right. The one con is that random exploration can be inefficient. Okay. Then another pro is that it provides guaranteed exploration, while fixed epsilon may waste exploration late in training. All right. So you need to be aware with about familiar with the pros and cons so you can make the best decision at all times. Okay. Um or okay. So here we have number 4, we talk about SARSA. SARSA simply means state action reward, state action. That means in a particular state, you take an action and you get a reward, which takes you to a new state with its own set of actions. That's why it's called SARSA. So that's on policy temporal difference control. And the overview is this: SARSA updates the action value Q of SA using the action actually taken by the current policy. So the on policy part of it is that the policy used to generate the behavior is the same one being improved. So it learns the value of the current policy, including exploration steps. And the algorithm is like this. For each step time t, step t, observe the state at that time, the action at that time, and then the reward at the next step, and then the state at that step. Then you choose next action at plus 1 using the current policy, which is epsilon greedy on Q. Then you update that, and so the updating is done as this. So Q of st comma at, will be then leading to, so all these other things you have on the right hand side leading to these new states. So alpha is the learning rate, while gamma is the discount factor, like we've always known. So the intuition here is that SARSA learns the expected return when the agent follows the policy used for behavior, thus inherently factoring in exploration risk. Then we have the behavior. So it's SARSA is more cautious in risky environments and may learn safer paths where risky exploration actions would result in poor outcomes. So you see, you are learning as you go, like in a particular state, you have an action leading to a reward, which leads to a new set of state and its own actions. So let's talk about Q learning, which is off policy. So the other time we talked about SARSA talks about on policy temporal difference, while Q learning talks about off policy temporal difference control. And in overview, Q learning estimates the optimal action value function Q star S comma A, regardless of the policy used to generate behavior. So you have off policy, it learns the value of the greedy policy while following an exploratory policy. So on policy, you remember, is actually the policy used to generate behavior is the same one being improved, right? But here, it learns the value of the greedy policy while following an exploratory policy. Yeah, keep exploring. So the algorithm is that at each time step, observe S sub t, A sub t, R sub t plus one, S sub t plus one. Of course, that R is reward there, while S is state and A is action. And then you have that update given by what you have right here. So the intuition for Q learning is that it aims directly at the optimal policy, okay? Assuming perfect exploitation from the next state, independent of the current exploration. The behavior is that it can learn more aggressive risk-taking policies, and it may overestimate action values due to Marx operator, which is a positive bias. So we now have expected SARSA, which is reduced variance temporal difference control. The motivation is that SARSA uses the sample Q of S. So Q at the next step, right? And action at the next Q of state and action at the next step, which introduces high variance. And Q learning uses the max, which can introduce bias. So expected SARSA updates now, results to this expression we have right here. So this uses the expected value over all possible next actions weighted by the policy pi and introduces variance and often leads to smoother learning. Then talking about convergence and practical considerations. So convergence conditions, you have sufficient exploration. So policies must explore all state action pairs infinitely often, e.g. decaying epsilon. Then you have the learning rate also, which also that's another convergence condition. The learning rate can also help. So the learning rate alpha sub t must satisfy Robbins-Monroe conditions, e.g., the summation of all the alpha t's should be equal to should be undefined, right? Meaning that the summation of all alpha t squared should be less than infinity, should be a real number, so to speak. So then we have a Markov environment. So stationary transition probabilities and rewards. So those are some convergence conditions. So when you have explored enough, when the learning rate satisfies a particular condition, and when you follow the Markov environment with stationary transition probabilities and rewards, then we have practical tips. For learning rates, start moderate between 0.1 and 0.5, possibly decay. So start with something and reduce it gradually towards zero. Then you have the discount factor, typically between 0.9 and 1 for episodic tasks. Then you have the exploration epsilon, start high, 0.1 to 0.3, decay to 0.01 or lower. Initialization, so you have optimistic initialization, can encourage exploration. Then function approximation, used for large state spaces, but convergence is not guaranteed, right? So we go on implementing SARSA and Q-learning on CliffWalking. So we are talking about the CliffWalking environment. So one environment we've been using is the frozen lake environment. So you assume you're working on a frozen lake, and of course that comes with a lot of care. And you have two possibilities. If you take it that if you take it that it is slippery, then you have a stochastic situation. If you take it that the frozen lake is not slippery, you have a deterministic situation, which is more which gives a better result. But the reality is that a frozen lake is almost always slippery, right? So then, but now we have another environment, cliff walking environment, which is a 4x12 grid with a start, goal, and cliff cells. Stepping into the cliff results in a large negative reward. Good environment to compare safety and risk awareness. So talking about the cliff walking environment. So algorithm steps, initialize Q table with zeros. For each episode, reset environment. For SARSA, select action A naught via epsilon-greedy. For each step, take action AT, observe R ST plus 1. Then for SARSA, select next action A sub T plus 1 via epsilon-greedy. Update Q according to the respective update rule. And repeat until episode ends. So I'm comparing SARSA and Q learning on a custom maze now. So for the policy lend, right? SARSA, which is on policy, and Q-learning is off policy, right? For SARSA, you have policy that includes exploration actions. For Q-learning, you have optimal greedy policy independent of behavior. Then you have behavior in risky environments. So SARSA lends safer paths that avoid risky exploration moves, while Q-learning learns shortest paths that may risk dangerous states during learning. Then you have the learning speed. SARSA sometimes slower due to cautious updates. Q-learning often faster but can be unstable or overly optimistic. Then you have variance of updates now. So variance of updates is higher and it's sample based for SARSA. It is lower due to max operator, but bias introduced. In Q learning, there's a max thing you're doing along the line. So if you remember what's in Q learning here, yeah, you see this gamma maximum of Q, whereas in the other case, you just have gamma Q directly, not the maximum necessarily, right? Um, so example insight in CliffWalking, SARSA tends to avoid the cliff by accounting for exploratory slips. Q-learning aims for the shortest path and may occasionally fall off during exploration. So it's more like you're climbing a cliff, and these two approaches you have them there: the space action, state action, reward state action, or Q-learning on its own. So Python implementation with that dataset example now, since okay, we have some warning regarding gym. So we have put lines 5 and 6 there to take care of that. So import numpy as NP and import gym. Okay. Gym is an OpenAI thing for that is good for reinforcement learning. So we define up epsilon-greedy, Q state the number of actions and the epsilon. So if np.random.rand is less than epsilon, we return return np.random the number of actions. Else return np argmax q state like that, and then we do that. Then we now define for SARSA. So we do all this whole thing for SARSA, environment, episodes, alpha, gamma, epsilon, and all that, all the Q and all the rest of them like that. So all the maths we've talked about, that's what we have coming here. Then we have the Q learning now. So Q learning, of course, we're comparing SARSA with Q learning. So we also do about the same, following all the maths we've done previously. Then we now define the policy evaluation, right? We do all that here. Then we print the policy, and then we try to run that with all the different results. So I can do the running now, and then it gives us all the various results we should get. Okay, so of course it was training SARSA, training Q learning, evaluating SARSA policy. Average total reward over 100 episodes is minus 17. Evaluate Q learning policy. Average total reward over 100 episodes is minus 13. Okay, so uh we have minus 17 compared to minus 13 for SARSA and Q learning. So for SARSA learn policies, you see, as you go like that, you have down, 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 left, left, down, down, right, right, and all that. Here you have left, left, down, down, right, down, down, left, 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 down, left, like that. So that's the Q learning learned policy. So interpretation of the results now. So SARSA and Q learning learn action value functions, Q tables by interacting with the CliffWalking environment over many episodes. Evaluation, we test each learned policy by running it greedily, no exploration for 100 episodes, and number of exploration for 100 episodes, and record the average total reward, just like we've seen the minus 17, minus 13 for each of the policies, right? Then higher or less negative. So less negative rewards mean better policies that avoid falling off the cliff. So it means the less negative, the better. So that means Q learning has a better policy with minus 13. So minus 13 is less negative than minus 17. So the higher, the better. So Q learning policy has the better result in this particular situation. So visualization. So the printed grid shows the best action in each state as arrows left, down, right, up, illustrating the learned path the agent prefers to take from state to goal while avoiding the cliff edges. In short, the average reward measures policy quality, and the arrow shows the agent's navigation strategy learned by each algorithm. Okay, summary table. The aspect, we have the policy type. All right. So SARSA is on policy, QLearning is off policy, while expected SARSA is on policy. Then update targets. For SARSA, we have that formula there. For QLearning, we have max. I think max is what distinguishes the two. Maximum action. So for QLearning, you're using the maximum action. That's why the result is expected to be better than that of SARSA. But for expected SARSA, we have some summation thing thrown into the mix. So exploration during update, SARSA considers exploratory action, while QLearning assumes greedy action. Then expected SARSA, yeah, it's expected over exploratory actions. Risk sensitivity, SARSA is risk aware and so it goes for safer policies, while Q-learning is risk neutral and aggressive. Expected SARSA has reduced variance, smoother updates. For convergence, SARSA has you have proven under standard assumptions, while Q-learning convergence is proven under standard assumptions also, and expected SARSA you have something similar to SARSA. So convergence is also proven under standard assumptions. So that's some idea about model-free control in reinforcement learning. So with this, I come to the end of the video. Let me know how helpful this video is for you. And if there's something you'd like me to try out along the line, let me know. If you have subscribed already, thank you so much for subscribing. If you have not, be sure to do that right away. Hit the notification bell also as you subscribe so that you can always get alerted each time a new video is released. On my channel, you can now become a member. There are different layers of membership. So you can click on join and you find three different possibilities of being a member that you can sign up for, right? You can download my code sheets and data sets so that you can look at these codes more closely and try to draw inspiration from them. Then try to tweak some of the values so you can really understand what is going on in those places. And I think that's really important. So like and share also this video and every other video on the channel so that more people can have access to the content I have going on here. Till I come your way again, keep doing data right. Bye.